Morning, everybody. So, a couple of things. I've decided to put the inverted lecture off until Friday because I really, after thinking about it, I don't want to start chapter 17 and then you all have a week off and then come back to 17. So I think it'll just work better that way. A couple of you have mentioned that you have things on Friday. I'll work with you. Don't worry about it. But I think it's going to work out better. So what I'm going to do today is catch up and talk a little bit about some additional stuff that we need to talk about out of chapter 16. I know it says chapter 21, Matthew, but it's the old book, okay? So we're going to talk about the Wittig reaction, and we're going to talk about the addition of primary and secondary amines to carbonyl-containing compounds and what functional groups we get from those, okay? So let's go ahead and get into that. The Wittig reaction allows us to take a carbon-oxygen double bond and convert it into a carbon-carbon double bond very efficiently. Okay? It is a very nice reaction that allows us to take either an aldehyde or a ketone and make an alkene. Okay? You have to have two things for this reaction to work. First thing you have to have is either an aldehyde or a ketone, and the second thing is you have to have a Wittig reagent. Okay? What can you tell me about that Wittig reagent by looking at its Lewis structure there? Pardon? Okay, where's the nucleophile? On the carbon, that's right. We have a carbanion, and we know that carbanions are going to function as nucleophiles. What else can you tell me about that reagent? Huh? Turns out it actually is fairly stable. Why is it fairly stable? Now, if we have a normal carbanion, right, they're not particularly stable. But is this a typical carbanion? It overall has a charge of 0, right? And why is that? That's right. We have a positive charge on the phosphorus. And so overall, this is neutral. But when we look at it atom by atom, we notice that the carbon is a carbanion and the phosphorus is a phosphonium ion. Okay? And so we have what we call a zwitterionic species. Okay, there's zwitterions in a lot of respects. Okay, so the Wittig reagent will react, and the carbon component of the Wittig reagent will become this piece right here that's highlighted, and you get your carbon-carbon double bond, and our byproduct is triphenylphosphine oxide. Notice how the reaction arrow is drawn. How is it drawn? One direction. This is essentially an irreversible reaction. It goes to completion very, very well. Can anybody tell me why we would draw this as going completely to the right? What do you think, Matthew? Okay, that's true. What else? Everything does have an octet. Okay. Everything has an octet in the starting materials, though, too. What do we need for something to go completely to the right or go to completion? Okay. Why? Okay. So we've got to be talking about something on the right being a lot more stable than the stuff on the left. What do you think it is? Think so? Alkenes have weak pi bonds. Huh? So, I mean, if I go, well, I'm going from a weak pi bond to a weak pi bond, I wouldn't say that that should go to completion. What else is up there that you're ignoring? Triphenylphosphine oxide. That's exactly right. What do you know about a phosphorus-oxygen bond? It's very strong. This is the linkage, right, that holds your DNA together, right? It's a very strong linkage. And so you're going from a weak, relatively speaking, oxygen double bond to a very strong phosphorus-oxygen double bond. The equilibrium is going to lie way far to the right, and essentially we consider this to be an irreversible reaction, okay? The cool thing about this reaction is that the double bond will be exactly where the carbon-oxygen bond was. There's no rearrangements here. That's nice, okay? Wherever that C double bond O is, that's where the new CC bond is going to be. Now, before you had the Wittig chemistry, how would you have made that alkene from that carbonyl? Let's say it's an aldehyde. How would you have made a carbon-carbon double bond from an aldehyde before today's lecture of learning about the Wittig reaction? What tools in your toolbox would you have used? Ah, very good. We would have used a Grignard. So we would have taken the carbon unit that we want to incorporate, and we would have made a Grignard out of it. And we would have added a Grignard to an aldehyde, and when we do that, what would our product be? A secondary alcohol. And then what would we have done to get the alkene? How do we get alkenes from alcohols? Dehydration, right? And what do we use for that dehydration? We can use H2SO4. It's a very good choice, right? That is what you would have done up until today. What is the problem with that, though, in the dehydration step? We can't have rearrangements, and we don't know. The double bond can be in a couple of locations because of whose rule? Not Markovnikov. Zaitsev's rule, right? Zaitsev's rule. And so we end up, if we do the elimination, we're going to get the most substituted alkene, right? In this case, you're always going to have that alkene where that carbon-oxygen bond was. You don't have to worry about Zaitsev's rule. And so that's why this is important to have this set. We could have made that exact alkene with other tools that we have, but it would have been multiple steps. This is one step. This is the easiest reaction in the world to do. You literally take the Wittig reagent, you literally take the aldehyde, you put them in a flask with a little solvent, you stir them, you come back in about an hour, and it is done. And you typically filter off the triphenylphosphine oxide, which is not very soluble in the solvents that we typically use, and voila, you've got a product. Okay? So that is the Wittig reaction in general. So an aldehyde or ketone plus a Wittig reagent gives me an alkene. That's the top layer of information that you need to know about this reaction. Okay? So here's a few examples. You can have what we call instant ylid. That's not an actual name, but this is what most people refer to this because you can buy it. And you just take this and instantly add it to your carbonyl, and you can get a new carbon-carbon double bond. In this case, since there's no other carbon substituents on the carbon of the Wittig reagent, you end up with a terminal alkene. And if we were to do this by the Grignard chemistry, right, we would have, well, in this case, we would have still gotten a terminal alkene because both of them are equal. But if we had more carbons out here, you would have ended up getting the more substituted alkene, right? So easy to do. The yields, I've done a reaction similar to this. The yields 95% or better. Usually you're low, you lose a little bit just to purification, but pretty clean. You can have substituted Wittig reagents where you have another carbon group, and you can do the chemistry, and you can end up with carbon-carbon double bond there as well. Again, yields are quite good. Yeah, Harrison.
Is there a limit to how many carbons?
You have two.
You only have two?
Right, because you can have two carbons on that carbon of the Wittig reagent. You got to have a bond to the phosphorus, and then you got to have the lone pair.
Okay.
So that takes care of all your 4 valences or your 8 electrons to account for the octet, right? So you can have up to 2 substituents on the carbon of a Wittig reagent. Okay. Now, you will quite frequently hear me refer to these as ylids. Y-L-I-D-E. An ylid. This is what the Wittig reagent looks like. Triphenylphosphine, you got your benzene rings on there. The phosphorus is positively charged. The carbon is negatively charged. We frequently abbreviate them like this. Remember, pH is an abbreviation for the phenyl group, right, or a benzene ring. And it's an ylid. And an ylid means that you have a positive charge on one atom and the adjacent atom has the opposite charge. These are ylids. Okay? They are nucleophiles. Okay? and you can also call them Wittig reagents. Okay. Now, like I mentioned, you can purchase a number of Wittig reagents. Um, you will also quite frequently see me write them not like this, but like this. Okay? I am not violating anything in doing so. Why am I not violating anything? Okay? But what about 5 bonds around phosphorus? Doesn't matter there, right? Why not? Because it's not in the second period, right? So the octet rule doesn't apply. I can have 5 bonds around phosphorus, right? And so you will quite frequently see me on an exam write them like this because it's a lot easier in my drawing program to draw this than it is to put in all these charges. But what you need to recognize when you see this is that there is a negative charge on the carbon and a positive charge on the phosphorus. We call this the ylide. What do you think we call this? The ylene. Okay, so you can draw them as an ylide form or an ylene form, and in fact, they're really just resonance structures of the same thing. In both cases, the carbon is going to be the nucleophile, and the phosphorus is going to bear the positive charge. Okay. Now, it turns out that you can't buy all Wittig reagents that you want, but it turns out that they're extraordinarily easy to make. Okay? So if we take triphenylphosphine, phosphorus has a lone pair of electrons. It's going to function as a Lewis base and a nucleophile. And we react these with an alkyl halide, where the halogen is typically bromine or iodine. Chlorine will also work, but it's kind of slow. Okay? If I take triphenylphosphine and I dissolve it in something like hexane, or diethyl ether usually, actually, and I take a primary alkyl halide, primary works best, and I mix them together, I get an SN2 reaction. And this reaction, again, extremely easy reaction for you all to do. Okay? The chemistry is very easy to understand. The nucleophile comes in from the back, kicks out the leaving group, and I form a salt, what we would call a phosphonium salt. You will hear organic chemists quite frequently refer to these incorrectly as Wittig salts, because we're going to make Wittig reagents out of them. But that's not correct terminology, but it's just kind of the normal organic slang. Okay? Now, if we're running this reaction in diethyl ether, is diethyl ether polar or nonpolar? Slightly polar, but it's pretty much so considered a nonpolar solvent. It doesn't dissolve in water, right? Okay, so it's fairly nonpolar. And do you think salts are going to be highly soluble in nonpolar material or insoluble? Insoluble. But the neutral stuff, soluble or insoluble? Soluble. So Sarah comes in, she takes her triphenylphosphine, she dissolves it in diethyl ether, she adds her alkyl halide and dissolves it in the diethyl ether, she mixes those together, and she stirs it, and all of a sudden she starts to see this white stuff fall out of solution. What do you think that white stuff is? It's the phosphonium salt. And she just watches it until she doesn't see anything else fall out of solution. And then she just simply filters it, washes it with just a little bit of fresh diethyl ether, she dries it, and she has the phosphonium salt. Easy reactions to do. I quite frequently have undergraduates that come to work in my lab make our phosphonium salts for us. Number one, it's cheaper than me buying them. And number two, it's a reaction that you can't screw up. And if you screw it up, then I usually ask you to find another lab. But I've never had anybody screw this reaction up. You can't mess it up. The only thing you can do is actually spill your reaction. And then you get the broom out and you sweep up your salt and we try to purify it. Okay? It's that easy. Okay? But is that a Wittig reagent? Paige, is that a Wittig reagent, that Wittig salt? It is not. And why is it not? I've got the positive charge on the phosphorus, right? But what am I lacking? I'm lacking the negative charge on the carbon, right? This thing has an octet. So how am I going to get the negative charge on the carbon? What do you think, Brienne? What am I going to have to do to get a negative charge on that carbon? Pardon? I'm going to have to remove a hydrogen, right? How am I going to remove that hydrogen? What reagent might I use to do that? A base. That's exactly right. Do you think I need a strong base here or a relatively weak base? Relatively speaking, weak. Okay? Sometimes you can even use sodium hydroxide. Okay? If it's a particularly stabilized illid, which we'll talk a little bit more about later. But typically you can use something like sodium hydride. A lot of times chemists will use butyl lithium, which is overkill, but they use it because it's convenient. It's a liquid. You can just inject it in and you're done. Okay? So we've got to remove that hydrogen on that carbon with a base. Okay? And so they say a strong base, okay? Again, butyl lithium is usually overkill, but sometimes hydroxide doesn't work, okay? But sometimes it does. So it just depends on the pKa of this hydrogen. Do you suppose the pKa of this hydrogen is going to be lower or higher than a typical alkane? Think it's going to be more acidic than a typical carbon-hydrogen bond or less acidic than a typical carbon-hydrogen bond? More acidic. And why do you say that? Huh? Okay. That's the observation that lets us know that. What's the rationale, though, based on the structure of that phosphonium salt that suggests that it should be a stronger acid than a typical CH bond? That's exactly right. That positive charge is going to stabilize the resulting anion, right? And anything that stabilizes the anion of the conjugate base makes it a stronger acid, right? Makes the conjugate acid stronger. So, yeah, we can get away with this. And so typical bases, again, that are used are things like butyl lithium. Not always necessary, okay, but usually convenient to do so. And so you end up with the illid and you're ready to go. So from an alkyl halide, you can make a Wittig reagent and you can make an alkene, as long as you have access to some triphenylphosphine to do that. And triphenylphosphine is dirt cheap. You typically order it by the kilogram, and it typically costs you more to ship it to you than it did buy the stuff to start with. That's cheap. Okay? Can anybody tell me what is a drawback of the Wittig reaction? Let's go back and look at a Wittig reaction. What would you say would be a drawback of this particular reaction? What do you think, Chance? I'll tell you right now that industry doesn't like to use the Wittig reaction if they can avoid it.
You're not very likely to get the triphenylphosphine oxide back if you use it in another Wittig reaction.
That's exactly right. The phosphorus-oxygen double bond is so strong that there's no way that you're going to get that back as triphenylphosphine, at least easily, to use in another Wittig reagent. So that becomes waste, and we have to throw it away. Okay? So it's not very atom economical. Look at all the atoms in triphenylphosphine oxide. There's 18 carbons. There's 15 hydrogens. There's a phosphorus and an oxygen. And if we add all that up, is that low mass or pretty high mass? Pretty high mass. So if you take something simple like acetaldehyde and CH2, for example, it turns out that the waste quite frequently weighs more than the product that you're making. Okay? Now the moles don't change, but if I'm having to throw away more mass than I'm getting in product, that means I'm having to build equipment that can handle a lot of mass just to throw something away, right? It's not very practical on an engineering scale. But on a laboratory scale, we love this because it's so well behaved. We know wherever that carbon-oxygen double bond is going to be, that's where our new carbon-carbon double bond is going to be. Okay? And it works really, really well for that. Okay? So, given that, starting with that alkyl halide, I want to make that alkene using a Wittig reaction. How do I do that? Take a moment, talk with your friends, come up with a solution for me. Can't do Grignard here. Why can't you do Grignard?
Because of the,
I don't have an ether.
oh, the ester.
I have an ester, right? So if I generate a Grignard on that ester, it's going to react with itself, right? So I can't do that. Wittig. The German pronunciation.
Are there like any American names or
Is there any what?
said, are there any like American names rather than like everything in Russian and German?
The Masterson reaction? No, I'm kidding.
I mean, I just like,
All right, how are we going to approach this problem? We're going to go in reverse. That's exactly right. It's the first thing that we need to do, right? So we know we want to make this molecule, and we know we want to make it from a Wittig reaction. And I know in a Wittig reaction, wherever my carbon-carbon double bond was, right, or is in my product, that's where I need to have a carbon-oxygen double bond in one of my starting materials, right? So I find the double bond I'm trying to make, and I imagine cutting it in half, right? So part of that partner has to be an aldehyde, and part of it has to be my Wittig reagent. Which part is going to be the aldehyde, and which part is going to be the Wittig reagent? The aldehyde is going to be this part, right? So I know this is going to be benzaldehyde. And how did I know it had to be an aldehyde and not a ketone? Because when I look at this carbon, I know it's got a bond to a carbon and a hydrogen, right? So I need that partner. And I need that Wittig reagent. And if I have both of those and I mix them together, I'm going to get my product, plus triphenylphosphine oxide, right? Okay. Do I have that? No. But I can make that from this plus triphenylphosphine followed by treatment with base, right? So Karina would take triphenylphosphine, she would take this ester, she would do the SN2 chemistry, she would get the Wittig salt, oops, OET. We're not at a Wittig reagent yet, but we're close. What base would you use, Brian? I would use sodium hydroxide here probably. I would probably take this, dissolve it in water, mix it with some ether, and add a little sodium hydroxide. And why will it work here? Why don't I need a really strong base? Because this carbon is adjacent to a positively charged phosphorus, like all Wittig salts are, but it also has a carbonyl next to it, right? That's going to doubly stabilize, if you will, the resulting anion. That anion is resonance stabilized through the carbonyl, and it is charge stabilized by the positive charge on the phosphorus. You can wash these with very mild bases like dilute sodium hydroxide, and you can get the reaction to occur. Okay? You don't have to use a strong reagent. This exact reaction we use just about every day when I was a postdoc, something that you're learning every day as sophomores in organic chemistry. We made a lot of these. These are known as cinemates because they come from, they're derivatives of cinnamic acid, cinnamon. We made them, but we had other substituents on the ring that we needed to do additional chemistry. And we'll talk about other things that we can do with them later. But very easy to do. You mix these things together, voila, you're done. In this particular case, notice the stereochemistry of the alkene is what? Is that cis or trans? It is trans. The Wittig reaction is only selective for trans if you have a stabilized ylide. This is a stabilized ylide by resonance. The Wittig reaction, if you have an unstabilized ylide, will give you a mixture of cis and trans and actually favor the cis a little bit. And that's another drawback to the Wittig reaction, is that it can quite frequently give you a mixture of cis and trans, okay? But sometimes it doesn't matter what you're doing, okay? I mean, sometimes you can have a mixture and take it on to the next step and be okay. What's another important point about this reaction? We're making what kind of bonds? Carbon-carbon bonds. Exactly, right? So that's important, as you all know. Sir. What protecting group would you use? And okay, so you would put the trityl where? Where would you put it? Instead of an ethyl ester, maybe a trityl ester? Okay, so you'd have a lot of bulk there, and maybe that would slow it down. It's possible. But protecting groups inherently, right, are wasteful and add steps. So I won't say it's impossible, but it might be impractical. Okay. The chemistry is pretty straightforward. The nucleophilic carbon attacks the carbon of the carbonyl, breaking that weak pi bond. You get to what's known as a betaine intermediate. Notice we got the positively charged phosphorus, the negatively charged oxygen. We've made the important carbon-carbon bond at this stage. The negatively charged oxygen will react with the positively charged phosphorus, because phosphorus can have more than an octet, right? And we form this four-membered ring, which is called an oxaphosphatane. Intermediate has been detected in these reactions. Why does that make sense to do that? Because we know the phosphorus-oxygen bond is strong, okay? And so we can form that strong phosphorus-oxygen bond, and now what happens, you push two arrows like this to where you get the phosphorus-oxygen double bond, or the phosphine oxide, and you get the carbon-carbon double bond.
How do you detect stuff present in the reaction, like in the middle of it? You just run it like while it's going through the NMR or something?
You can. Actually, these reactions can be run at low temperature in the NMR, and you can detect the various species as they're formed. Yep. You can also, there's a technique today called, Dr. Donahue has this, it's called React-IR, which has a probe with a diamond tip that you can actually stick into the reaction. You can watch the IR as the reaction is proceeding. So when you're starting off, you'd see your carbonyl, and as the reaction proceeds, you would see the carbonyl disappear, and you would see the presence of a phosphorus-oxygen double bond starting to appear in the fingerprint region, I think is where it appears. And you'd start to see the carbon-carbon double bond form. So you can actually start to see these various species form during the reaction by monitoring it with IR or NMR, those kinds of things. Yep. So you can do a variety of different techniques to actually detect these things these days. Okay. So pretty simple mechanism, at least in terms of the arrow pushing, right? Nucleophile attacks electrophile, or Lewis base, Lewis acid. Lewis base, Lewis acid, and then pushing 4 electrons around to eliminate the triphenylphosphine oxide and get the carbon-carbon double bond. And it prefers to form a carbon-carbon double bond, even though all of those are sigma bonds in that oxyphosphatane. Why? Ring strain. We've got a strained 4-membered ring. Very good. And even though we're getting a weak pi bond, we're gaining a strong phosphorus-oxygen double bond, right? And so all that would suggest that we're going to have the reaction go completely to the right. Okay? So that's the Wittig reaction. Again, one limitation is that quite frequently you will end up with a mixture of isomers. So if we look at this particular case, we've got our ylene, or the Wittig reagent here. We've got an aldehyde. And since we actually have a hydrogen on this carbon and an alkyl group, we can imagine these being either in a E form, or sort of a trans form, or a Z form, right? And in fact, you get almost a 6-to-4 mixture of those isomers. Okay? And it slightly favors, in this case, the E isomer. Just a little bit. Okay? But we get a lot of the Z as well. Why do I say that that's a limitation? Okay? They are different compounds, right? They have different melting points, different boiling points. They are physically different, right? So it looks like we might have a problem there.
And now just come out with more weight.
Yeah, if what we wanted here was the E isomer, we'll get 60%, at best we'll get close to 60% yield, right? Because we're going to throw about 40% of it away, because we don't want that Z isomer. Or if we want the Z isomer, we're going to isolate only about 40% and throw 60% of our stuff away, right? However, it turns out that a lot of labs will still use this chemistry, because a lot of times what you're wanting is to make a carbon-carbon bond, and a lot of times what you want is a carbon-carbon single bond, right? And so what would I do in that case? Let's say that what I'm interested in is forming a carbon-carbon single bond here. Well, I can do the Wittig chemistry because it works so well. I get a mixture of isomers, and then what do I have to do to get my single bond? I add hydrogen across it, and I just hydrogenate. And both of these then go away and become the same product, right? So a lot of chemists will actually use the Wittig chemistry to make the carbon-carbon bond where they want it, and then reduce it, and it no longer matters. And that's what we were doing when I was a postdoc. We got horrible mixtures. We got like 1-to-1 mixtures of the E and Z, but I was doing nucleophilic addition that got rid of that stereochemistry. It didn't matter. Okay, so I did the Wittig chemistry, got the mixture, and then my product was structurally what I wanted at the end, because I was destroying the stereochemistry of the alkene anyway. So it didn't matter. You can make beta-carotene, and in this case, we're going to get pretty much so exclusively the trans product, not much of a mixture here. You have a little bit of the cis. Can anybody tell me why in this Wittig reaction we'll get mostly the trans? It's conjugated. That's right. So if I draw it as the ylide form, where there's the positive charge on the phosphorus and the negative charge on the carbon, I notice that it's resonance stabilized. Okay, and so I'm going to get the carbon-carbon double bond in the trans format, or form here, pretty much so exclusively. And how would we detect that this reaction is occurring? What do you all know about beta-carotene? It's orange, that's right. So we would take the aldehyde and the ylide, which are, they might be slightly yellow, but they're not highly colored. And then as the reaction proceeds, we get carrot orange. And you just monitor that color until the color quits increasing, and you know that the reaction's over. That's right. Uh-huh. Would beta-carotene be safe to ingest? Sure, you ingest it every time you eat carrots. But if you made this in the lab, I would not trust your skills to make sure that you don't have any contaminants in there. I mean, I wouldn't want to be eating triphenylphosphine oxide, and I wouldn't want to be eating an aldehyde or an ylide that might be present in trace amounts, right? So if you were to make it this way for human consumption, it would have to go through a whole series of tests and processes to ensure its purity. So let's suppose you want to take cyclohexanone to that alkene. And let's suppose I told you to do this chemistry before today, before you learned about the Wittig reaction. You would do Grignard chemistry, right? And so what you would be tempted to do would be to take the cyclohexanone, react it with methyl magnesium bromide, a Grignard reagent, because we need to put in just a single carbon. That will give us the tertiary alcohol, very good yield, right? You would then, as Gabby suggested earlier, take sulfuric acid and you would eliminate water. But the problem is you would get this as your major product. Probably about 90% of it would be this. And only about 10% or less would be this. Because of whose rule? Zaitsev's rule. And Zaitsev's rule says that in the elimination of water, right, we're going to eliminate such that we get the most substituted alkene because it's the more stable alkene, right? So you're going to get a product that you want as a minor product. That's not very efficient. But if we do the Grignard chemistry, we get exactly what we want because we know that the carbon-carbon bond is going to be exactly where that carbon-oxygen double bond was, right? You're just really changing out the oxygen for a carbon. Okay? Very, very efficient chemistry to do. Okay? Let's talk a little bit about the addition of amines to carbon oxygen double bonds or carbonyls. Okay? Remember, we can have primary, secondary, and tertiary amines. You already know all that, right? And it turns out that if you take an aldehyde in particular or a ketone and you react it with a primary amine, you're going to get what's known as an imine. It's also commonly known as a Schiff base. And so what you're going to do is you're going to take the carbon-oxygen double bond and you're going to replace it with a carbon-nitrogen double bond. This typically requires mild acid, so mild actually that if you wash your glassware with acid, it's usually enough acid on the glassware to make this reaction occur. That's how I always do these reactions. I'll soak my glassware in a dilute solution of sulfuric acid or hydrochloric acid for a couple hours and then put it in the oven and let it dry. And there's usually enough residual acid on the glassware to make this reaction occur very well. Okay? So, high level of knowledge here. Primary amine and an aldehyde or a ketone gives me a imine. It is a condensation reaction because we're losing water. The amine attacks. You end up with what's known as a carbanolamine intermediate, and then we simply lose this hydrogen and this OH, and we get the carbon-nitrogen double bond. Okay? It's a Schiff base. It's a very easy reaction to do. This is a reversible reaction. So how can we make the reaction go to the right? What do you think, Russell? How can I make the reaction go to the right here? I could add lots of reagent. That would do that. That's one of the things we can do in Le Chatelier's principle. That might be kind of costly, though. What can I do that's cheaper? Pardon? To make it go to the right? But I could take the water away, right? So you guys have used drying agents before in lab? You've distilled things. Water boils pretty easily, right? So maybe we boil the water out, and I can drive the reaction to the right. How would I make the reaction go to the left? Add water. That's right. And so these are reversible reactions. Okay? The chemistry here is quite similar to the Wittig chemistry, except we don't have phosphorus around. The amine simply attacks the carbon of the carbonyl. You end up at the carbanolamine intermediate, which then the OH from the carbanolamine intermediate picks up a proton from that mild acid. You now have the oxonium ion, which is a good leaving group. The electrons now from the nitrogen come in to form the pi bond and displace the water as a leaving group, and you end up with your product. And notice everything is reversible. Okay, so we can make amines very easily, and we can destroy them very easily by playing with Le Chatelier's principle. And this turns out to be biologically relevant. This is how you're seeing the slides right now. It's through imine chemistry. So, I am by no means an expert on the eye, but this is what I understand, all right? So you have rhodopsin, right? And rhodopsin is a protein called opsin, which has a primary amine that is linked through an imine linkage to, basically this is an antenna that can pick up photons. Where does this come from? What's good for your eyesight? What do you eat that's good for your eyesight? Carotene, that's right. That kind of looks like part of beta carotene, right? And it is. That's where it comes from, okay? But notice it has a single cis double bond. And it's not very stable because there's crowding here, right? And so when that antenna picks up a photon, that photon transitions an electron from the ground state to an excited state. And in doing so, it breaks that weak pi bond. And when that happens, what can happen? You can get free rotation of that cis bond to a trans bond, okay? And so picks up a photon, you isomerize the cis double bond into a trans double bond. That changes the structure. It basically tugs on the opsin protein when that happens. I'm saying tugged very generally here, okay? And that results in a nerve impulse. That's how you're seeing things. However, if we look at that exact equation as it's written up there, that's not shown as reversible, is it? So you should be seeing a slide for a few milliseconds and then go blind. But fortunately, the imine bond is reversible, right? So once this happens and we have the nerve impulse, there is an enzyme that helps hydrolyze this carbon-nitrogen double bond back to the aldehyde, which then gets displaced, and a new fresh one comes in and forms the new carbon-nitrogen double bond. So that's how you regenerate this in your eyes, okay, through this reversible process. And so it's kind of nice that imines are reversible. It allows us to continue to see for many years, okay? So what you're learning in class is relevant to biology, okay? Secondary amines will also add to aldehydes and ketones, but you don't get imines, you get enamines. Enamine, and they're important molecules. The first step is exactly the same. We get to a carbanolamine. But why is the second step different? Why, with a primary amine, do I get an imine, and in a secondary amine, I get an enamine? What's different? What's different in that second step? Has something to do with the nitrogen. What's the difference? That's right. There's not a hydrogen on that nitrogen to eliminate water and give the double bond between the nitrogen and the carbon, right? So that can't happen. But where do we have a hydrogen? On the alpha carbon, right? And so we can imagine losing a hydrogen here and the OH and giving us our double bond here and getting what's called an enamine. So a primary amine plus an aldehyde or a ketone gives me a imine, and a secondary amine gives me a enamine. That's right. And a tertiary amine, no reaction. Okay? So these reactions too are very well behaved. They typically require mild acid, just like the imine formation. So a ketone plus a secondary amine, I get this enamine. This is acetone. We can get that enamine. Okay? We're forming carbon-nitrogen bonds in both of these reactions, but in the secondary amine, we're forming an enamine, which is a single bond between the carbon and the nitrogen, and the enamine, or the imine, excuse me, with the primary amines gives me a carbon-nitrogen double bond. Okay? So again, the mechanism is very, very similar. This part 1 is the same as part 1 for imine formation, so nothing new there. The difference is here. The oxygen gets protonated again. We now have a good leaving group, right? These electrons can come in and kick that out, and you end up with a positively charged nitrogen, but that's not stable. And so now water comes in and functions as a nucleophile, or as a base, I should say, displaces this hydrogen. These electrons come here, Those electrons get pushed up onto the positively charged nitrogen, and you end up with the neutral product. Okay? Why don't we just have the base come in and remove the proton here and go straight to the product? Why do we go through the intermediate where we have this iminium ion, if you will? Why do you suppose it has that extra step? Because on paper, right? On paper, I've got this as a good leaving group. I could just simply draw the water coming here, displacing that, and get straight to my product. That's easier on paper. But this is actually detected. We know that this actually exists. Why? Why? We don't have a carbocation, no. It must mean that this reaction actually occurs faster than this reaction, right? Why? Okay, carbon has an octet here, here, and here. Why do you think that this occurs faster than this coming in and just displacing the water as the leaving group? It is a good leaving group. But why does that mean as part of the answer? Takes what?
It takes time to work across the whole molecule, which just leaves
Okay, that's really close to the answer. So if we look at this, we've got a Lewis base and we've got a leaving group that are connected in the molecule. It's right there. This will kick that leaving group out. This has to actually travel a distance to do its chemistry, right? So that's going to take longer time. So that's why it's the rates. So this is right there. The concentration is as high as you can get it. Chemistry occurs. And then this can come in and give you the enamine. Even though on paper you could show a perfectly good mechanism why the water should just come in, take that proton, water leaves, and you end up with the enamine directly. But we know it doesn't happen that way from all the experiments that have happened. And it turns out that when you have that good leaving group and that tertiary amine, you're going to get that chemistry occurring very, very quickly. Okay? And so that's why you end up with this nitrogen with the positive charge as an intermediate. Again, completely reversible. All right, we're out of time. You all will need to finish looking at the stuff for chapter 16. We've already talked a little bit about the addition of water last time and the addition of alcohols as hydrates and acetals. Go back and look at that again. And Friday we will have the inverted lecture on this stuff. So